Hi, everyone. So we start with our first, no, not first, second, third practical session that we have during the Neural 2025 workshop today. This is going to be on the DeepDisco, deep disconnectum. My name is Anna Matsulevits. You probably met me and hung up with me in the past couple of days. I used to be Michel's and Thomas' PhD student long time ago, about a month ago. And yeah, today I'm going to show you part of my PhD work, which is on the deep disconnectum. And to give you a little bit of a background, I'll start with my next slide, if this is going to work. Namely, I looked into the ischemic stroke. So my work focused on the ischemic stroke and the outcomes and disconnections following ischemic stroke. And in ischemic stroke, it's, well, if you know, but probably like just the basic, overview is if it happens basically when a clot blocks the blood flow in an artery, and that leads to oxygen depletion and eventually to cell death and at some point to a lesion. So depending on which artery is basically blocked in the brain, we have a different, different brain parts that are not being supplied with oxygen, and that can lead to a wide range of impairments, starting from motor, cognitive impairments, language impairments, and up to emotional impairments like depression and anxiety. And so you heard a lot about the disconnectum and disconnectivity, and as those different lesions or different clots cause a different lesion and basically knock out one part of the brain, of course, the white matter connections in that part of the brain also get disconnected. So Michel gave you a way better introduction on that earlier, but just to sum up, depending again on where exactly the stroke happens in the brain, we have different white matter tracts that are affected. And since white matter tracts can be associated with a wide range of functions or different functions, it also depends, of course, of like which white matter tracts are disconnected and which functions might be impaired. So if you were sleeping during Michel's talk, this is just a very quick summary of how we are computing the disconnectum, the original or like the BCB toolkit disconnectum, right? So we have a lesion or a stroke in that in the first place. That leads to a lesion that we put in a MNI space. And we had in the BCB toolkit, we have an average tractogram of over 100 tractograms of healthy people. And then we basically overlap this average tractogram with the binary lesion, and we check basically for each voxel, okay, is that lesion cutting through a certain tract or not? And that produces or outputs as a disconnectum, so a probability map, a 3D probability map for each voxel in the brain, showing the probability of that voxel being disconnected or not disconnected, depending, on the lesion. So the only thing with this is great, right? But the only thing is that it takes pretty long to compute. So the BCB toolkit is open source and a great tool, but it takes a while. So we thought, why don't we just replace this by AI, right? So we were thinking, okay, let's take some fancy deep learning algorithm. In our case, not that fancy. If you know a little bit about machine learning, deep learning, it's a 3D unit. It's just like the very standard, very basic, the most basic thing you can do, which I did as my first project during my PhD because I just didn't know any better. So we thought, why don't we just replace this long computational step with a deep learning model and get from the lesion directly to the deep disconnectum. And that's exactly what we did, but it didn't look as fancy as here. This is just like a random GIF I found on like an artificial neural network. How it looked like was more like this. So this is the 3D unit model architecture that we used. It's called unit because of its U shape, right? So we have like an encoder part, a decoder part. And to start with, what we trained this model on was, first of all, the binary lesion mask. So we had the binary lesion and a disconnectome template, so that the model basically knows, okay, how do disconnections look like in the brain. So that's why we have here, like, as an input, a 2, because we have 2 channels. And essentially, like, all those artificial neural networks, we have like multiple different layers of interconnected units. And the goal is, to go basically from the input to an output that we provide. And the output that we provided was the BCB toolkit disconnectomes, right? So we wanted to go essentially from the binary lesion masks to the disconnectomes and train the model for that based on 1,333 synthetic lesion disconnectome pairs. So that was like our ground truth. That was our original data. We trained that model on. Synthetic lesions, okay? Synthetic, that's a good point. The reason why we did synthetic lesions was to increase the variability, because stroke is known to not happen just randomly in the brain, right? If you have like a heat map of different stroke lesions, it's like usually the middle cerebral artery that is affected. So it's not like just randomly, but in order to increase the variability, we took synthetic lesions that were basically also matched in the hemisphere and in the size with real lesions, but they were synthetic in the sense that they were distributed randomly in the brain, and then based on that we computed the real disconnectomes and used that as our training set. We could have also done more than 1,333, but we just chose that number because we had 1,333 real lesion disconnectome pairs, and those we used then for testing. So essentially we could have also trained it on like 10,000 or 30,000 lesion disconnectome pairs, and it would have probably been even better, but it worked with 1,333 as well. So you're probably really excited to see what actually the results look like. And that's what they look like. So we found out after training and tweaking the model, we found out that our 3D unit actually accurately resembles the real BCB toolkits disconnectomes, okay? So you can already, this is just a random example to show you, but it actually depicts pretty nicely, the main disconnected tracts. And the only difference that you might be seeing here is that the deep disconnectomes look a little bit smoother, right? So they look as if they're not capturing everything. Or they might also be getting rid of some noise. So this is, I'll come back to that later. But we were really happy to see those kind of results, first of all. And the correlation with the real disconnectomes was over 0.8. So it was a pretty satisfactory result we obtained. Another example I want to show you is the frequency of disconnected voxels. This is presenting essentially a difference or a flaw or drawback of those deep disconnectomes, because here you can see what kind of structures the artificially produced disconnectivity maps are not capturing. So if you just look at the frequency of disconnected voxels for the real disconnectomes, this is how it looks like. And for the deep disconnectomes, you can spot that the big main tracts, or if you can call them main tracts, are disconnected way more often than those little U-shaped association tracts. So this is maybe an indicator of, okay, we are capturing the main information but not capturing maybe those fine-grained things. However, the visual comparison is already, well, we can't really rely only on the visual comparison here. So we asked ourselves what we can do with, having the deep disconnectome next to faster processing times, right? So we can now produce a disconnectivity profile within a fragment of a second, whereas with the BCB toolkit, it takes, it takes 720 times longer, actually. So I'll walk you through a framework where we used the deep disconnectomes and where we actually proved their that they work better for some tasks or like for some analysis. So the question is what we can do with having those disconnectivity maps, right? And you heard already like on the applications of disconnectomes. Namely, we can associate disconnectivity with function and thus with neuropsychological scores. And how we do it is by creating a latent disconnectome morphospace with UMAP. So that's how a UMAP, that's essentially just a dimensionality reduction algorithm. So you take like a bunch of big data. Big data is basically a disconnectivity profile because it's 3D, right? It's if you create a vector of like one 3D picture, it's going to be a very, very long vector. So we have a bunch of data. And in order to reduce that bunch of data and make sense of it and still keep like some kind of, relation, how different data points relate to each other, we can use UMAP. Exactly as you can see here, first it starts with like a random cloud of data points, and then it, depending on how similar or dissimilar this data is, it tries to cluster it together. Okay, that's the main point. So we took our 1,333 deep disconnectomes that were produced by the trained model, so the real lesions and like artificial disconnectomes, to create this space. And what we obtained from it was that. Okay, so this is a 2D latent morphospace where you have all those different disconnectivity profiles. Each disconnectome is a point here in the space, and depending on how similar or how dissimilar those disconnectomes are, they will land either close together in that space, okay, or further apart. And that's what you can see. Can you see my cursor? No, you can't. But that's what you can see essentially here on those three examples. So you have like disconnectivity profiles. They look all different, right? And they're also placed at different places in that morphospace. Okay, that is the idea of a latent space. Now, what we like having that mapped out in a space, what we can do with it is that we can embed new patients into that space, right? So imagine now we have a completely new set of patients who have a lesion, just a lesion. So we have them from Vienna, for example, okay? We have 100 patients who have motor scores and a lesion. And we can embed them we can embed their disconnectivity profiles into that space. So they will land, depending on how their disconnectivity profiles look like, they will land somewhere in that space. And if we have their scores, their neuropsychological scores, so let's say we have motor scores for that cohort, we can correlate basically their location in the space with their score, okay? Am I having everyone here? Okay. That's important. So we can correlate the space with their scores. And what we can get from that correlation is basically a heat map. So let's say score 1 is a motor score, okay? And if now the majority of the patients who had motor impairments, so who really were impaired in their motor scores, land somewhere here, we have basically obtained a heat map for that score, representing a risk area for that function, okay? This is, let's say, motor function. For another function, let's say language, that kind of heat map would look completely different, okay? So, for example, those people or those disconnectomes who landed here and were impaired in their motor abilities, they might absolutely not be affected by language, okay? So having now these kind of heat maps, we can just apply a basic, so it includes PCA and then multiple regression, but like basic statistics at the end. I will not go like deep into the stats here, but we can apply basic statistics and then predict a score for an entirely new patient again, okay? So having those heat maps based on patients who have their scores, we can get an entirely new cohort from London and say, okay, we have those disconnectivity profiles, let's predict their scores. And this works. It's actually the framework of Lia Talozzi, published in Brain 2023. She did it with the real disconnectivity, like real disconnectomes, the Michel disconnectomes. We call them sometimes boomer disconnectomes. So she did that with the real deal, with the real ones, and showed already that this is like a really, really good way to predict neurofunctional outcome after stroke. And in order, so because I was comparing the deep disconnectomes visually and like with like voxel-wise correlation and all the other stats, I was comparing them to the real disconnectomes because that was my ground truth, right? And I showed, hey, we actually perform and resample them really good, as you could see on the previous slides. The second interest was like, okay, will they perform as good in the prediction of neuropsychological scores if we insert the deep disconnectomes into the same framework, right? And what we found out was that they actually outperformed the real deal. Okay, let that sink in. So the fake ones, let's call them fake, is a little bit maybe that's negatively connotated, but the deep disconnectomes that were produced by the AI model, basically the deep learning model that I trained, if inserted into the same framework, they actually yielded more accurate predictions for neuropsychological scores. And we're talking long-term neuropsychological outcomes, right? It's like 1 year post stroke. Yeah.
Is this because your real ones are less variable?
We're getting there in a second. It's a very good question. Very, very good question. Yeah, because we asked ourselves the same question. So yeah, you can see here that like there's a significant difference essentially for 86 neuropsychological tests. So we had like not only motor or language or anything, but like 86 different tests. And with all of them, taking all of them together, we have a significant difference here between the deep disconnectomes and the BCB toolkit disconnectomes. And obviously we asked ourselves exactly that question because nobody believed me, okay? Everybody was like, yeah, she just started her PhD. She's probably like, she messed something up. So, like something is wrong here. So we asked ourselves, why are those predictions better? And since it's based on this morphospace, on the UMAP, right? Because we're mapping them out and relating them to each other, we had to look at the two different morphospaces because we have one morphospace for the BCB toolkit disconnectomes and a different one, obviously for the deep disconnectomes. Yeah. 2D.
It's just 2D.
It's just 2D. Yeah. So here, that's exactly it. These are 1,333 deep disconnectomes, and they're all in a 2D space. Yeah.
Could you increase the dimensionality by including other variables, for example?
You can, yeah, you can, but that also increases the complexity, of course. But yeah, you can essentially, increase the dimensionality, but it does not necessarily increase the prediction accuracy. We tried with like adding flair as well.
More difficult, right? Because the model would be more complex. So.
That's right, but doesn't really necessarily.
You set it.
Yes, you can do with UMAP. You can also do more dimensions, but yeah, it's easier, like the easiest, basically. We started with the easiest way, and then yeah.
So, in the 2 dimension, can you associate to something like biological or something, or they are just the complex analysis like CCA?
You can, yeah, you can. Lia did that in her paper. I didn't do that, but you can also associate basically associated to different tracts as well, yes.
No, I mean, what is two axis mean? You know, or there is just mathematical space?
This is just a mathematical space, yes. Like the two axes, the UMAP1 and UMAP2, you can't associate basically to any, like, to anything in the brain biologically in that sense, but you can obviously look at, okay, which kind of disconnectivity profiles, like what kind of tracts are disconnected more like, you know, in this cohort versus the other cohort. And then you can basically make sense of it. Yes, Eduardo?
Maybe like, I don't know, lesions related to right hemisphere or left hemisphere tend to land in one part of the subspace, maybe figure out if there is some quality into these.
Yes. Again, I didn't do that, but Lia did do it, and she showed, yeah, that's explained very well in the brain paper of hers. But yeah, she looked into different hemispheres and so on, and essentially it's also, well, the disconnectivity profile, right? This is going to be
This split between hemispheres mapped into this space, for example. Or
I don't know. I'm not sure whether it's well, it's not mapped per se, so we didn't map the split of the two hemispheres, yes. But I think you can you'll be able to basically associate like one hemisphere more to like one cohort and like disconnections in the other hemisphere to another cohort. But then again, you can have some of like, for example, commissural fibers, right? And they will be maybe somewhere. Yeah. So okay. I will continue with why those predictions were better than yeah, the original ones. So for that, we looked at average Euclidean distances in those two spaces. Okay, so we had the average Euclidean distances from, bless you, from each point, so each disconnectum to every other disconnectum in that space. Okay, and looking at those average Euclidean distances, we calculated the difference between the ECB toolkit minus the DeepDisco, the morphospace distances. Does it make sense? I know it's hard to read that graph, but you're going to understand in a second. So you can see that the difference is basically smaller for, okay, sorry, let me rephrase. What we found out was looking at the difference between the distances was that for close distances in that space, so for dots that are close together, this difference is actually bigger because it's in the negatives, okay? The difference is actually bigger. And for far distances in the space of for far located dots, the distance is smaller in the DeepDisco, okay? So speaking from the perspective of the deep disconnectum morphospace, the dots that are in the cluster, so the disconnectums that are in the cluster, they are actually segregated better, okay, than the ones than in the space in general. This is not really okay. Yeah, it's a little bit hard to grasp. So we take a look at the cluster. We're speaking of DeepDisco, okay, and we take a look at the disconnectivity profiles that are similar, okay? They're clustered together, they're similar. And what the graph is actually saying is that for the deep disconnectum, within the clusters, the distances are bigger. However, between the clusters, so between those two here, the distance is smaller, okay? Am I having everyone on board here? Okay. So that means basically that within the clusters, the dissociation between similar disconnectivity profiles is better, and between the clusters, it's worse compared to the BCB toolkit. Okay.
You said that within the clusters, the distance is bigger, right?
Exactly. The segregation is better within the cluster. Yeah.
Is it also able to create like subpopulations within the cluster?
Yeah, like essentially that is it. Yeah, like I wouldn't say that creates subpopulations within the cluster, but exactly. So the segregation is just better for similar disconnectivity profiles. Okay, and those are harder to actually, keep apart.
But the key is, can it be like subprofiles inside the? due to
What do you mean by subprofiles?
so there's a cluster,
Right,
and the segregation is better dispersed with DD. So
exactly.
it is also able to create like subprofiles inside the one profile.
Inside one profile, subprofiles. I'm not sure I'm getting your question, but these are like each of those dots is already a disconnectivity profile, right? So yes, if you would model, like I guess if I don't know if that's your question, but if you would model basically something in between, I think that would be that would be more like possible. Then if they're not segregated as well, because it basically merges, one kind of disconnectivity profile together. Yeah.
So do you think that's, for instance, for that reason, BCB toolkit would be, for instance, better at predicting single cases, and this could be better at predicting like group level comparison?
That is a good question. We have not tried that. That would be interesting to see, actually. Yeah, we have not tried that. But so my point here is that it worked better with the DeepDisco because the segregation within the cluster, so with similar disconnectivity profiles, worked better. You might say now, well, but like the similar, like the clusters between the clusters, it worked worse. But the thing is, for the prediction, it doesn't really make, like it's irrelevant, right? It doesn't really make a difference because those are already so far apart. They're already segregated, right? The two clusters here, for example, they're already kept apart. So it doesn't really make a difference if they're like a little bit closer together for the DeepDisco morphospace. It doesn't affect the prediction. Whereas within the cluster where we have like a lot of similar connectivity profiles, if it's segregated better, that is actually what makes the difference and what leads to a better outcome prediction 1 year post-stroke. Okay, do I have everyone on board here? Yeah, cool. That is cool. If you wanna read about that a little bit more, you can totally do that. It's for free. Open source and all. And to just sum up on the background of what we're going to do now is that we found out that the 3D UNet accurately resembles the BCB toolkit disconnectomes and does that 720 times faster. So within like literally a fragment of the second, you'll have a disconnectivity profile. The DeepDisco significantly outperform the BCB toolkit disconnectomes in stroke outcome predictions, and AI-driven models for clinical settings might enhance the efficiency. Yes, Aline.
I have like a weird question.
There are no such things as weird questions.
The prediction of the neuropsych tests is so powerful. Would a system like this one be able to create synthetic neuropsych profiles of specific disconnectomes? Because you already can predict them. I would imagine that, if the prediction is so good, you potentially can also create synthetic scores.
Yeah.
Because that would basically mean that you can create
A disconnectivity profile, basically. So you would do like the inverse. You would go from the score to a disconnectivity profile.
Yeah, you can.
Yes.
Create the norms of the disconnectome and.
Yes, you could like in theory you can do it. We did that as well, not with neuropsychological scores and disconnectivity profiles. We did that with different methodological approaches for stroke outcome prediction, but that's exactly the same idea. So we had a morphospace, right? And since this is like a mathematical space, you can always do the inverse, exactly. So you have basically a space, and obviously, the best thing would be if we had, for example, those 1,333 disconnectomes and they would fill up the entire space, okay? That would be the ideal case, or like they would fill up every possibility there is. But since we don't have that, and the UMAP, dimensionality reduction algorithm, still creates a 2D space, it basically fills in the missing data, okay? It fills in the missing gaps and relates, based on the relation of like how dissimilar those disconnectivity profiles are.
Yeah.
Exactly. So you can do the inverse. How reliable that is, that's a different question. But you can basically do, you can go back into the space that is created and basically go to the disconnectivity profile that might be mathematically associated with yeah, MJ.
Sorry, I just have a more data-driven
Yeah,
question.
of course.
But so you put your disconnectivity maps to do the UMAP. But
Right.
what's the format that you're like? So you vectorize your map, but what's this vector?
So that's the disconnectivity profile. All the disconnectants are in MNI space. Okay.
Yeah.
So they're all already, standardized. And I flattened
Okay,
the entire
vectors.
data, like for each participant or each patient in that case, I had the disconnectivity profile, flattened the entire profile. So I had a vector of, I don't know how many voxels there are in, but that's probably Flavio knows probably how many voxels there are in a standard space. And then I had a matrix, a huge matrix of.
Did you try, so when you train your units to create your disconnectivity maps, this unit, it creates a latent space of its own with the embedding. So it creates interpretation of your disconnectivity maps.
That's right.
And did you try a dimensionality reduction on this
No.
latent space?
No, not in that one. Yeah.
Very related question.
Yeah.
How big is the actually the space to use your name? So you started from the old voxel of the map.
Yeah.
You go down to something smaller.
Yeah.
And then you go up again and you want to regenerate your.
So yeah.
What is the dimension of the latent space or embedded space?
That is 3D. So in the UNet, in the artificial neural network, that's a 3D UNet. Okay.
How long is the vector? 100 box and under within dimension, not just 3D dimension.
That's a question. That is for the artificial neural network you're asking. I think we reduced the dimensionality so that it is, or we actually gave the entire. So this is how it looked like with the channels and with with the reduction. But I gave the entire 3D image. So for to train the neural network, I gave the entire 3D image, and for the UMAP, I did the vectorization, like the flattening of the vectors and the matrix. Okay.
I was thinking you said that you wanted to learn. I was just wondering.
Yeah.
If you can maybe increase the dimensionality of the smallest or the deepest layer.
I hear you.
And you can actually get a high sharper resolution.
I hear you. Yeah.
That's it because you kind of. I don't know, that was just
No, that's a good call. The thing is, back then I had to, so my GPU that I had back then here was the massive size of 8 GB. And I had limitations when it came to, to basically applying and training models. Yeah, so I had to, basically go down on like a batch size 2 or stuff. Yeah. But that's why I couldn't leave it like, yeah.
That might be the reason why you have this kind of smoothing result at the end. Actually, you have a very narrow bottleneck there.
Yeah.
And all the information gets really compressed, and then you go back.
That's right.
And you regenerate it, which is fine.
Yeah.
It means it's working great.
Yeah.
You might reserve a little bit more information.
Yeah.
If you have a little bit more dimensionality, a little bit bigger vector at the deepest.
Yeah, yeah, absolutely, you might be absolutely right. That's worth looking into when I have the time for it at some point. But okay, guys, you want to try and do it together and get your own DeepDisco on your computers. Then, so we have you have to either go to the Git repository, which is just like GitHub, Anna Matsulevits, DeepDisco, or if you want to, actually, yeah, we'll do that because that's easier. And the important while you are cloning the repository, does everybody know how it works? If you go on GitHub and you can basically either just just download that folder, okay? Or you can clone that folder, like whatever works for you. If you're familiar with Git commands, you just go git clone and then you just copy the folder. Or if you're not familiar with it, then I think if you click here, you can just download it as a zip file, okay? And just download it, place it somewhere at your documents. Yeah. Yeah.
The projects,
Yeah.
the data we're working on is already in all that we download, right?
Yeah, there is example data. So I have example data in the folder so everybody can, make it work basically. So once you have that, I will assist whoever, with anything that is if you run into any issues. But essentially how it looks like, okay. So in the DeepDisco is we'll do it together in a second. I just wanna walk you through the very, very simple interface that I created. So we started with the whole brain model back then, but then we also trained the same neural artificial neural network for the different types of fibers. So we have commissural fibers, we have projection fibers, and association fibers. So this is the first window you'll see. You will select your model, okay? You can either do whole brain disconnections or you say, hey, my favorite fibers are the commissural fibers. I just want to look at the commissural fibers. So you select the model and then, and this is like the second, essentially really the second window you will see where you can load either, like very, very simple, okay? This is just literally 4 buttons essentially. So you can load either a lesion mask. You'll have some in the example. I'll do it now, I'll do it in a second also on my computer, so you can just follow it here. You can either load a lesion mask or an entire lesion mask directory. So you don't have to do it if you have I don't know, 30 or 40 lesion masks. You don't have to do it one by one. You can just select an entire directory or do it per lesion mask. You select an output directory if you want to. If you don't select one, then it's just gonna place your outputs in the same directory as where your inputs are coming from. So yeah, well, good practice to select an output directory to just not get messy. And then if you see, oh, I actually don't want to do projection fibers, I want to do the whole brain, then you can just change the model as well, and then you press generate deep disconnectome. Okay, this is fairly easy. Yeah.
There's no threshold.
No. So this is but you can do the thresholds in FSLIs later on, because this is usually how I look at disconnectomes and how I look at brain data in general. So you can do it in FSL. Okay, does everybody have the folder DeepDisco in their favorite folder on their laptops? Really? Awesome. Okay, you know what? Then I will actually show you how it looks like for me, at least. Okay, depending on your operating system now. Okay, so this should be the folder, right? You see that stuff. Okay, so if you're working on Windows, you want to, so we do the manual installation, okay? Because it's that seems to work for everyone. I had a nice other, just like a click solution, but it doesn't work for everyone. So we're just gonna go with the manual installation. If you are on Windows, you want to run manual installation .bat, okay? If you're on Mac or on Linux, you're gonna open your terminal and run bash manual installation pip, okay? And if you do that, then okay, if you do that, then something like this should be happening. So a virtual environment folder is created in that folder, and then it starts downloading all the. Yes, all good.
For Windows,
So for Windows, it's the manual installation Win. Okay, sorry, I can also increase the size here. Win. Okay. And I think you just click on it, right? Right, Stan? On Windows, you can, if you're using Windows, you just click on manual installation _win, okay? This is your file. If you're using Linux or Mac, then you want to run the manual installation pip, okay? Of course. You know what? I'm gonna come over and show you. Oh, nice. I like what I see. Very nice. All good, don't worry. Okay. Perfect. So I'm gonna go to the terminal. Yeah. Oh, they had to. I didn't run. Yeah, I get. I Thanks. Here's yes. Dropbox by any chance, or is it in your on your local?
There we go. We're always down to
Just wait for it. I guess. Yes. So once you This, I do. Yes.
Ah, then go dash and I didn't know that.
It's what counts also. So you can do it.
We can yeah, exactly. That makes
Yeah, it's just because you haven't No, no, yeah. Yeah.
So
I know from science that directory.
okay, so in order to finish in time, if if it hasn't downloaded yet on your computer, you probably have a partner next to you who has it on their computer. So just yeah, you can just maybe follow it on their computer. It's also not complicated or anything, but I think to show you what you can do with it and how to basically operate it. So you should be able to see something like this, right? So here you can essentially select one of the models, then this other pop-up window will pop out. And in order to load a lesion mask, you click on load lesion mask and you'll have in the example folder. So there is a folder, it's called examples or something. You'll have 4 different nifty files that are example lesion files. Okay, they're like binary lesion files. You click on like either, yeah, whichever you're interested in, and then whatever you prefer, really. Like you can do for the whole brain, you can just. Sorry. As you prefer. If you want a 1, then you select go on. Oh, sorry, it's not in the. Then you say load lesion mask. If you want to select the entire directory, you select load lesion mask directory. Okay, you can either do the entire directory or you can do each of them separately. You'll see in the here you'll see the selected model. So here it's now projection fibers, but depending on which model you selected, it's going to be something else. And then you just press generate deep disconnectomes, and it will be there in your either selected output directory, or if you didn't select an output directory, it will be in your input, so in the lesion mask directory where the examples are named, also according to which model you selected, so whether projection fibers or something else. And yeah, you'll see your file. Yeah.
Can you type it?
Go again, sorry. Okay, so you know what I'll do? Sorry? So we'll do it together, okay? I have here my. Okay. I hope this is still my screen that I'm sharing here. Okay, so we have here this window, okay? This is, okay, you guys have the window. I select commercial fibers, then my window changes to that pop-up, okay? I load the lesion mask. Here are the example lesions, okay? I click on that. Sorry, this is, I have like a bunch of stuff generated here, but I select the example one, okay? You have example 1, 2, 3, and 4. You have 4 examples in this directory. I open that lesion. I see the loaded example here, all right? I can also increase the size. So you see the example 1 selected. You see the commercial fiber model selected. I have no output directory selected. You know, for good practice, I might just do that. So I'll go here and say, for example, I want to have it on my desktop directly, okay? I see my output directory, which is users, my name, and desktop. And then I click on generate deep disconnectomes. And my disconnectome is done, okay?
The model is.
It is fast, huh? And here I can see now my output, which is also named after my selected model. So it says example 1, DeepDisco commercial fibers, okay? Now I gonna just close all this. Go open, for example, eyes. Open fossilize. And now I can simply drag and drop it in here, okay? I will select, you know, I want it to look hot, so I will select this. In order to, so we just orientation-wise, you know, if you know fibers, you'll get what kind of fibers are disconnected here. But in order to orient have a little bit better orientation, we can go to File and FSLIze, add standard, and then you can add a standard like MNI space, let's say just like a T1, 1 millimeter. And here you go, okay? You have it on the brain. So you have already a slightly better orientation. Everybody followed? Okay. If not, you go on File and FSLIze, yeah, to add standard. And then if you click on that, you'll have like the entire directory of like all the standard brain images in FSLIze. So you'll have this. Another cool thing that you can do with it is I hope actually Vale is that also on Zoom? Like, can you see this as well on Zoom? So it shares my entire screen.
I'm seeing the.
Okay, great. That's awesome. Okay. I will hide all these panels here because we need, in order for you to see what I want you to show for the last 5 minutes, and then we're done. So here we kind of, okay, so who can tell me what kind of track that is? Great. But if you're not experts, like you are, you can also use atlases to help your orientation. And FSLI is a great tool. We can add an atlas, okay? And how you do that is by going to settings, okay? Like here in the upper left-hand menu, you go on settings, you select ortho view, and you check atlases, okay? You have this long drop-down menu. You can check on atlases. And what that does is giving you here, down here, an entire list of different atlases for like either cortical atlases and subcortical atlases, but also extract atlases. And these extract atlases are tracked atlases. Here I would like you have some for macaques, which we don't need really here, but what we wanna do is we don't need the structural or the subcortical, cortical structural atlases. What we want to select is the extract HCP probabilistic tract atlas, okay? If you have that selected, you'll see it here in this next box, and you'll click show, and that makes it appear on our brains, on our standard brains and our deep disconnectomes. Why that is cool is not only you see, the different tracts here, in order for it not to overlap with your deep disconnectome, you can click this black dot here and you can only see the outlines. You can also change the width of the outlines. And essentially, you can now click on any of, the tracts that are in the extract HCP atlas, and it will show you right here, you see it, what tract it is. Okay? You can see it here. Right here. Yes. Right here. Sorry, I was highlighting it. So basically navigating the cursor along the space here, you can basically see, even if you don't know what kind of tracts might be disconnected, you can basically check it out and yeah. No, the percentage is because it's a probabilistic tract atlas, the percentage is just related to the atlas, but it's a cool orientation. Like, if you don't know what exactly is like going on here, where the deep disconnectome is showing a disconnection, then you can, orient yourself.
No,
with
why
that.
the standard option is not available on, like it's.
Because you probably installed FSL wrongly.
It's in the, can I open it? It's in the anaconda, but it doesn't allow me to select this one.
The standard, the atlas,
The standard option, like it's given, but I can't.
because you did not download it probably. So I think if you download FSL properly on your local system, then it has everything, like all the dependencies, all the options. But yeah, sometimes with Anaconda, sometimes it doesn't work for me either.
All right.
So yeah.
Example.
So you have look, there are like little, do you see the arrows?
Yes.
So you select one thing, and then you can choose basically the layer. You got it? Perfect. Awesome. Very good. Awesome, you managed as well. Okay, so we can play around with it. You can still continue playing around with it, but I need to end my presentation and find it actually. So there's nothing else I can teach you. So this is it. Actually, this is a little test because you've been hearing so much about all the different tracts and fiber classes. So we have an input lesion. This is, the different, I did that for the presentation. I selected those 4 different models, right? And produced an output with those 4 different models that are provided in the DeepDisco toolkit. Can somebody say what kind of fibers these are here? Projection fibers, exactly. What about that one? Very good. Connecting the 2 hemispheres. What about the one on the left? What kind of model can that be? Uh-huh. Yeah, you see all the disconnections there. So essentially then the last one are the association fibers. Okay, so yeah, this is what we just did, right? We looked at the at our outputs, we selected atlases. We looked at the atlases to overlap with our outputs. This is what we just did, what you can do. And if you're interested in reading more about it, or like reading a little, kind of a README file, which is a paper, we have a paper on it as well. So thank you very, very much. Sorry for being 5 minutes late here. And yeah, I hope it was cool. Thank you. If you have any questions or you run into issues with the installation, let me know. I'll be around in the next days as well. And happy to, you know, assist and play around with stuff and even do like statistical analysis if you're interested. All right. Merci.